In this video, I'm going to talk about the test for convergence called the p-series test. This is actually a really easy test if, in fact, your series is a p-series. So what a p-series looks like is 1 over n, so our variable is going to be the base of the exponent here, to some p-value, some power, which would expanded kind of look like this. Has two conditions. If p is greater than 1, if that value here is greater than 1, then the series converges. If it's between 0 and 1, then it diverges. If it's a negative in the denominator, then it's exponential growth, and that's just going to diverge. If it equals 1, then we have 1 over n, which is harmonic, which we've already established, diverges. So I'm going to go ahead and prove this to you, but past this, you just need to know those two conditions when given a p-series. So for this proof, we are going to use the integral test. Okay, so we replace our n with an x, and p is some power. Now, it should be noted this is going to be, p will be anything except for 1. If p is 1, then we have the harmonic series, and we've actually already done that integral test to show harmonic divergence. For any value except for 1, we can use the power rule, which is easier recognized if I rewrite that x to the p as x to the negative p. Then apply the power rule, which again works if everything except for 1 there. Okay, so go ahead and add 1 to that power for whatever value of p is. My power is now 1 bigger than that, but we know because of our power rule, we also need to divide by that value. I'm going to pull out the 1 over p minus 1 because that's just a constant. So whatever happens on the inside, the constant isn't really going to affect that. But we're going to have b to the negative p plus 1 minus 1 to the negative p plus 1, which is just going to be 1. Okay, so the part that we're interested in is this part here. So I'm going to kind of come back to, this is the integral we're looking at, but the part that we're interested in is what happens as b goes to infinity of b to the negative p plus 1. And it depends on what our p value is. Okay, if our p value is between 0 and 1. Okay, if I plug a value between 0 and 1, then this, say it's a 1/2, that means negative p plus 1 is going to be a number greater than 0. Okay, so how does that help me? That means that the limit as b goes to infinity of b to the negative p plus 1, if this is a positive value and we're raising a big value to a positive value, that's going to be exponential growth, which is going to be infinity, which means if my p is between 0 and 1, we have a divergent series. If, on the other hand, my p is greater than 1, okay, if I plug in a value bigger than 1, say 2, I'm going to have a negative 2 plus 1, which is going to give me a negative value, which means that my limit as b goes to infinity of b to the negative p plus 1, I'm now raising it to a negative exponent, which is going to be exponential decay, which as we go to infinity goes to 0, which means the integral test converges, which means the series converges. So between 0 and 1, including 1, it diverges, but if it's greater than 1, it converges. So the p-series is an easy test to use if in fact your series is a p-series. So this first example we're looking at, is it a p-series? So we've got 1 over k to the 0.1. So our base is our variable to some power, yes. Okay, n to the negative 3. I'm going to go ahead and rewrite that as 1 over n cubed, because we're really looking for that structure, which is yes. Here, it's not to a negative value. This is no. Okay, we're looking for 1 over our variable to some power. Our power is the variable in this case. This one is no. In fact, this one is an infinite geometric series. So understanding the difference is important. 1 over n is a p-series. It's just the special case that it is also the harmonic series, which I will say for the 100th time, harmonic series diverges. Okay, so now that we know what p-series do and how they behave, we're going to determine if the series converges or diverges. It may help to rewrite your series. If it has a negative exponent, that's the same as being in the bottom. So this is a p-series where p is 4/3. 4/3 is greater than 1, which means this converges. The next one, it may help again to rewrite that power, or that root in this case, as a power. If we have the 4th root, that is to the 1/4 power. My p is 1/4. 1/4 is less than 1, which means this series diverges. Okay, we like these little p-series are often written this way. Okay, I can rewrite that as a rational exponent 5/3. Whatever the power is goes on top, whatever the root is goes on bottom. So my p is 5/3. All we care about is how does that compare to 1? It is bigger, so it converges. And our last one here, 1 over k to the pi. Our p is pi. Pi is definitely bigger than 1, so this one also converges. Okay, so then we have a multiple choice problem. The series 1 over n to the 2a converges if and only if. Well, according to the p-series, my power converges if the power is greater than 1. Not equal to 1. If it equaled 1, it'd be harmonic and diverge, so it is simply greater than, which means a has to be greater than 1/2, which is presented as 0.5. So notice there's a lot of 0.5's our only option. We want a to be greater than 0.5 so that our series converges. So that is the p-series test of convergence.